since the first hand. No.
Me too.
I sort of stayed in my office and tried to be productive. You know, the key part of it is trying to be, can't do it in a hack. But
Did you notice that I don't know if you on the list there's a happy hour coming?
yeah, yeah. So I will try to get out to that. Are you going out?
Yeah. We never know what to do.
We'll give it 2 more minutes.
No, I'm aware of like GISS time. Yeah.
It's standard time.
Yeah, you know, like give it 5 minutes or so.
Yep.
Oh, welcome back, Patrick.
Okay, so I think we can start. I'll briefly introduce our speaker. This is Jesse Nusbaumer, who got his PhD at CU Boulder in 2016. Since graduating, he joined GISS as an NPP postdoc working with Allegra. And today he'll be talking to us about water tracers. So go ahead, Jesse.
Thanks for coming. This talk will probably be on the short side, hopefully you're not too sad about, but, and you know, as you can tell from my chosen color palette, that'll be a very exciting talk, and very, hopefully hope you enjoy it and learn a lot. So let's get started. So this is a satellite composite of integrated water vapor, so right, like all the water in a vertical column. From the past few days, and you know, you can kind of see all the things we recognize, right? My mouse work? Oh no. Anyways, you know, you can see the ITCZ and the general like wet tropics, drier mid latitudes. You can see the tropical cyclone that kind of slaps Ireland a little bit here. So one of the questions that I'm interested in, certainly interesting things in the tropics, but I'm interested in these plumes of moisture that are kind of coming off, or at least they look like they're attached to this sort of tropical reservoir and then are traveling poleward. You can see them associated with the actual hurricane, but then also over here in the Pacific, and then kind of throughout most of the southern hemisphere, including crossing Australia, coming off of the South American convergence zone. So, at least in the western U.S., these have started to be described as atmospheric rivers. The reason being that they're long and they're thin and they carry a lot of water. The reason the west coast of the U.S. cares about them a lot is because they tend to be low in the atmosphere, around like 850 millibars, and when they are transported inland from the ocean, they tend to collide with the mountain ranges there, like Sierra Nevada or the Cascades or whatever's in Canada, and produce a huge amount of precipitation. In fact, most evidence is that most of the flooding events that occur in the western, basically the west coast of North America, comes from these atmospheric rivers. Which, if you're curious, are mostly dynamically driven by extratropical cyclones and frontal systems. So there's been a big push recently to be interested in atmospheric rivers from basically just an extreme events standpoint, or a sort of hydrologic forecasting standpoint. But I'm personally interested in another reason. So if you basically composite all of the events throughout the mid-latitudes and calculate their moisture flux, they represent almost the entire poleward moisture flux in the mid-latitudes, like over 90%. Given this, and given also their very small zonal spatial scale, like around 10%, they play a significant role in the global water cycle, right? And in turn, the global energy cycle. They, again, are responsible for almost all of the poleward moisture transport. You can see. Oh, yes.
How are they defined? I mean, does this include like when a tropical cyclone goes extratropical or something like that?
Yeah, the way that's actually an open debate on how you define it. The way they defined it is essentially if you're long and you're thin and you're, it's like you just take a, reanalysis or whatever, and you look for a moisture flux above a certain threshold, and then if you're like long enough and you're thin enough, then you count as an atmospheric river.
So like Ophelia is probably considered in...
Yeah, so in this, we'll go back. Yeah, so I'm assuming their algorithm probably counted Ophelia in this case, yeah. So, but it's not going to count, it wouldn't, so if you count anything that's long and thin and wet, you'll get the ITCZ, right? Because it's long and thin and wet. So they tend to, so there's usually then like sort of categorical things saying like, well, you have to have some sort of meridional angle, something of that nature. But yeah, no, but there's actually arguments about how that's calculated. But yeah, regardless though, it just isn't really that amazing of a statement. Most of the polar moisture transport is produced by baroclinic cyclones in the mid-latitudes in a very narrow region, not just kind of like a big diffuse thing. Okay, anyway, so whatever these features are, how we define them, there's since they're transporting all this moisture, transporting a large amount of latent energy, right, latent heating. And it depends then where exactly they're getting this moisture from. Are they evaporating it from like local, the local ocean, or are they transporting it truly from the tropics? And that's an open question. There's been numerous sort of studies to try to get at it, but they all kind of have conflicting arguments. And so, a common method is to use Lagrangian tracers. In other words, just particles you release in your model that follow the air mass, and then if you look at how the moisture changes in those particles, you can derive potentially where the moisture is coming from. The problem with this method, though, is that, again, it's following the air, it's not following the water. And so, even though you can use dq/dt, the change in the water with time, to try to back out where the moisture is coming from, you have to build a lot of assumptions into this derivative. You have to essentially you're basically losing a lot of subgrid scale information, or any processes that are occurring in the parameterizations of the model itself. Other methods have used these water tracers, which I'm going to talk about in weather models, to look at specific cases. However, the problem with any specific case is you don't know if is this particular weather event representative of the entire classification of the climatology, or do you just pick a particular kind of extreme event even for these extreme events. So this is a case of one of these atmospheric rivers that hit Norway and produced extreme flooding, but most atmospheric rivers don't go up to Norway, and so again, is this representative of the average, or is it just a fluke? So to get at this, we want to use climate models, right, that can really generate true climatologies of these events. And we want to be able to know where the water is coming from. Well, we know that climate models, right, have a water cycle. They have all of ocean evaporation, ET. They have runoff and precip and condensation. They might be missing the vitally important fog drip, but they have most of the processes that you would need to really capture where the moisture, at least in these atmospheric events, are coming from.
E3 has fog.
Does it really have fog drip? That's actually fun.
Well,
All right. Yeah.
but fog turbulent diffusion to the surface.
Oh, nice. Awesome. All right. Well, we now have all of the... Yeah. Fog. Got fog drip. Okay. All right. So, I want to know where the moisture is coming from. So one way you could do it is you could just say, okay, well, I'm just going to cover the entire land surface and make sure nothing evaporates from that region. Of course, if I did that, I would totally change the climate system, right? It would be, the circulation would change, the dynamics would change, everything would change. And so it wouldn't really tell me much about what's happening in the real world. So what I could do instead is just build a second hydrologic cycle in the model. And this second one goes through all the same physics that the real one does in the model, but it has no influence on the actual, on basically anything else. There's no latent heating or cooling, it has no influence on the radiation, no influence on sort of cloud microphysics or aerosol losses or anything like that. What this allows me to do then is I can then, are you working? Oh, I went too far. Don't look at that. Okay. What I can do is then I can actually modify the secondary water cycle any way I want to. So I can just shut off everything except for, say, evaporation from the ocean. And then I can allow this ocean evaporation to then go through and still experience, this X is kind of too big, but still experience condensation, rain out, all these things. So it then tells me where does the moisture that comes from the ocean reach without getting contaminated from, say, ET from land. And of course I could do the opposite. So as an example, here's a case of several water tracers from NCAR's model. And the colors are, so this is the Arctic Basin. You might be able to see Greenland here, and here's Canada and Eurasia. And there's 4 tracers here. The red one, which is now kind of showing up, is all the ET from any land surface. The purple is from the North Pacific, the cyan's from the North Atlantic, and then yellow is from the Arctic Ocean itself. And this is over a course of a year. I'm going to wait until it gets to the end. But you can see, so if 0 is January 1st, and this is now December. In winter, you're dominated by water that's coming from the oceans. Particularly, mostly, you have some Arctic Ocean water, but a lot of it's coming from the Pacific and the Atlantic. Just getting, again, infected poleward. However, as you get into the warm seasons, like June, July, August, the ET flux from land grows. And in fact, it reaches a point where most of the water in this model, most of the water over the Arctic Ocean is coming from evapotranspiration from land. So it's all land-driven sources. So these are the so with this tool, what can I really look for? Now I should say that even though, I'd like to think this is a really new advanced feature, it's actually quite old. And so actually the GISS model was literally one of the first models to ever do these water tracers, or these water tagging, back in 1986. And so here was their water tag simulation, where each one of these big boxes was one of these tracers, these tags, so all the water that came from Eurasia, or all the water that came from the North Atlantic. And the little boxes were where they looked at where the precip was falling. So from box 6, how much water came from Eurasia and the North Atlantic. I wish I could show you a cool plot from that, but it was just a table because, it's the 80s. And so But still, GISS was really one of the sort of pioneers of this method. And they've been able to keep it in the system for essentially the entire time, while most other models have lost it and had to regain it. Another sort of major development at GISS was actually done by Max Kelly for his PhD. So when he's not like building the entire model for us, he was figuring out a way that instead of having to instead of having to say ahead of time where I want my water tracers, I can just distribute them using spherical harmonics to basically cover the entire planet with water tracers using the minimum number of tracers one would need. And I realize it's kind of a busy plot, but essentially you can imagine you have 144 of these water tracers, and they're all distributed kind of like this. This is tracer 11 in this case. What this allows you to do is that if I'm interested in any region of the globe, I can just sum up all of these tracers. That's not just a summation, you have to do Fourier stuff. But when you add them together, you can then tells you for any grid point where the moisture source is coming from, at least to a resolution of this number of tracers. So, which I think is about an 8x5. I'd have to think about that. But what this does, it allows me that instead of having to know ahead of time, okay, what's the one I'm going to look at, I'm going to tag everything for it, I can just run the model, and then any region of the world I'm interested in, I can look at ahead of time. Or I can look at after the model simulation, which is much, much more useful. As an example of this, this was work done by Sophie Lewis, also here at GISS, back in 2010, where she looked at basically changes in past climates. And in this case, it's what's known as a hosing event, where you have a bunch of fresh water that's getting dumped into usually the Atlantic Ocean. In theory, because it should be melting glaciers, or melting ice sheets. And she found that for this particular region in Africa, for example, you go a shift away from Indian Ocean moisture to kind of more Atlantic-based moisture. And this is important, as we'll get to later, because these sources influence the water isotope composition. And the water isotope composition then is what is encoded in a lot of paleoclimate proxy records, which is what we then use to back out what the past climate system was like. All right, enough about other people. Let's talk about me. So, again, I'm interested in these atmospheric rivers, and I want to know where their water came from. So, and I'm interested mostly in the U.S. West Coast, at least for this particular study. So I split up the planet into all these little water tracers. And I'm kind of going to a priori assume that most of the water is coming from the Pacific, and so that's where I've mostly tagged most of my results. However, I want to cover everything, so I tag, the entire southern hemisphere, and then tag land areas, the Atlantic, other things. As a real quick, the results I'm going to show you are usually in ratios. This just means if I know that there was X amount of total water over some grid box, but 50%, half of the water came from, let's say, this one, then this thing would have a value or a ratio of 0.5. So then when you see the numbers, it just means the fraction of the moisture that came from each one of these boxes. And since I'm tagging the whole world, and it's just kind of a conservation statement, the ratio always has to end up equaling 1. Or if I summed up all of these tags, it should just equal the total water. So, just not that interesting. But here's the interesting part. So first, before I look at atmospheric rivers, I kind of want to know what's just the climatological average moisture source for the west coast of the U.S. And this is just a pure time average. So at any random time, if I was going to look out and figure out where the water is coming from, what would it be? It's really not that surprising. Most of the water, so again, we're kind of looking at this region. Not sure if I'm supposed to touch the screen, but I realized after I did that. But most of the water comes basically right off in the eastern Pacific, which makes sense, right? It's just kind of evaporating there and just being infected over. So do atmospheric rivers have any water distribution that's different from just coming straight off the eastern Pacific? And so this is the moisture source if I'm only looking at atmospheric rivers, which in this case is actually defined as simply the 90th percentile moisture flux over the western U.S. So it doesn't necessarily mean an atmospheric river. It could be any sort of extreme moisture transport event. It's just on most of the time, those are atmospheric river events. Anyways, so when you first look at just the climatological atmospheric river average, it looks just like the regular time average. Most of the water is coming from the eastern Pacific. Isn't that surprising? Although it does mean that if you look at the sort of satellite image, it looked like it was connected. It's actually not, right? It's not actually taking moisture from the tropics and sending it all the way poleward. It mostly seems to be local confluence or convergence of water. That being said, if you take the difference between the time average and the atmospheric river values, you get this result, which means that atmospheric rivers, compared to the time average, are pulling actually more moisture from the tropics, particularly the tropical eastern Pacific, and less from higher latitudes. So there really is a potential tropical connection, which is important because you imagine in the future, as the storm track maybe moves poleward or something, this could change, and you no longer maybe have that tropical connection. So that's the next question we ask. How does global warming change this result at all? And the answer is yes. But in a way we didn't quite expect at first, which is this is now the change in atmospheric river moisture sources just due to global warming. And global warming in this case is we ran a simulation at 2100 and we had a simulation from the year 2000. It's just a difference. What we found is there's a decrease actually in almost all eastern Pacific moisture source, but an increase in western Pacific and also even way out into Eurasia, the Indian Ocean, even the Atlantic, and even the southern hemisphere. And in fact, we found that on average, the distance, the sort of moisture source became more remote for any location as the climate got warmer. And this isn't just for atmospheric rivers. This is just a sort of, it seemed for this one particular model run, it seemed like a general statement. If you looked at any location, the essentially the advective length scale of moisture, or the distance that moisture is transported on average before it rained out, increases as the climate gets warmer. So moisture sources get more remote. Awesome. So that's kind of a cool result for atmospheric rivers, but it doesn't really mean anything for any other sort of climatological process. So another study I was involved in looked actually at Atlantic salinity. So, you know, you're not an oceanographer, which I am not. Apparently the Atlantic Ocean is getting saltier. And most coupled model projections suggest that it will continuously get saltier. As the climate warms, the Atlantic Ocean basin is supposed to increase in salinity. And one of the questions is, why is that the case? And we know that basically it has to do with the freshwater amount, the freshwater budget. And it's most likely going to be driven by a change in either P or E, precipitation or evaporation. So what's causing it? Is there more evaporation from the Atlantic that's just causing the basin to get saltier, or is the precipitation changing in a way that getting less rain relative to the evaporation amount? So we applied this water tracing technique, and what we found is that it wasn't even necessarily the change in evaporation, although it does increase because it increases globally due to global warming. A lot of that rain that came just purely from the evaporation fell back out over the Atlantic. So it didn't actually change the net budget. Instead, what happened is if you take the general amount of moisture that does evaporate from the Atlantic and you compensate for the fact that now the distance that this water is advected is increased due to global warming, more of it is getting advected over the Isthmus of Panama and then precipitating out over the Pacific, instead of raining back down on the Atlantic. So another way to say this is that instead of it being a surface flux change in the sense of an increase in evaporation, it's an increase in the amount of advection of moisture away from the Atlantic and into the Pacific. What this implies too is not only that the Atlantic is getting saltier, but if everything else was equal, the Pacific would be getting fresher. And I actually don't know if the Pacific's getting fresher, but I thought that was a really cool result. And so it matters even for oceanographers, not just atmospheric scientists. Okay, so another example of one thing I was involved in looked at the Congo River, the Congo River basin. This is the saddest plot I feel in all of science, because this is the number of stations, weather stations that are in the Congo.
Wow.
And, you know, you can see at the early 20th century, okay, we're, 1900, no one cares about meteorology, but now we're spiking up in the 30s, 50s, everything's looking good, we're building climatology, and then, whoops, everything basically goes to zero. In fact, right now, there's almost no weather stations in the Congo River Basin. It's not actually zero, but there's much less than what there was. So this makes, and the Congo is actually an important region, right? This is an area, the ITCZ is functionally over it. There's a lot of convection. It's important for the local tropical circulation. It's important to, and a lot of people live there. Millions and millions of people live there. It's important to understand the hydrology of the region. So one of the questions is, where does the Congo actually get its moisture from? In other words, is it mostly driven by the Atlantic? This is just wind vectors. This is surface, and this is, if you're looking at height. Anyway, so one of the questions though is most of the water that's coming in Congo's kind of here-ish. I should stop touching it. Is the Atlantic the major source? Because we know there's a lot of inflow from the Atlantic onto Africa. Or is it coming from somewhere else, like, say, the Indian Ocean? If they kind of over through this way. Because even though the Atlantic is strongly, advected onto land, of course, the general trade winds are going this way. And the Indian Ocean is known at least to have a major influence on East Africa. Maybe it gets farther inland. So if we go back to that Sophie plot, Sophie Lewis's plot, you can see that it is indicating that there is some oyster that's coming from the Indian, relatively less is coming from the Atlantic. And this is for 0K, which means 1850. So does that hold? And what we found was yes. In fact, for the climate models, in this case, this is NCAR's result and GISS shows something similar. The Indian Ocean actually seems to be the major moisture source for the Congo Basin, not the Atlantic. The reason being that we think the Atlantic, and this is just from the model simulation, but it looks like the Atlantic inflow is part of a sort of shallow sea breeze, so instead of like coming up and then definitely raining out, it just kind of circles through and goes back out again. Whereas the Indian seems to be cold up into the actual like centers of convection, of deep convection. That being said, there are issues with this. Particularly, there is a mountain range that's kind of right there that the models tend to flatten off, when in reality they might be, if you had a higher resolution model, you might be able to capture the orography better, and you might find that a lot of the Indian Ocean moisture rains out. So this is an open question. But, at least from the climate model's perspective, it's the Indian Ocean seems to be the dominant driver of moisture over, say, central tropical Africa. And not just on a climatological average, it also seems to control this seems to be the dominant influencer of interannual variability. So we found changes in the Indian Ocean, sort of SSC patterns and things like that, had a stronger influence on the tropical African moisture sources. Okay, so a lot of the stuff I did in my PhD, what am I actually being paid for here at GISS? But I'm supposed to, there you go. So I'm supposed to be looking at the Madden-Julian oscillation. And there's of course a lot of people who are looking at the MJO here. If you're not familiar with the MJO, it's sort of this 30 to 70 day incidence of enhanced convective activity, so enhanced precip, decreased OLR, outgoing long wave radiation. That tends to kind of form out in the Indian and then move eastward over kind of the maritime continent, eventually out into the western Pacific. And this figure makes it look like it's just some sort of Walker cell, but in reality this whole thing is moving this way, and then it dives down, and then at some point it comes back up again. One of the questions is what kind of initializes the MGO? What is required before one of these starts up and moves? One of the hypotheses is that you need this it's a moisture mode. In other words, you need this buildup of moisture in the atmosphere, and you need to get the atmospheric column wet enough before convection can kind of survive as it convects, I guess, vertically, without entraining too much dry air and dying out. So we'd think that if this is the case, then water tracers should show us that. And so that's what I'm working on essentially right now. And so here is a little animation of the OLR from, this is NOAA, so this is just the observed. And actually, this isn't just the pure OLR, this is massage OLR, we'll just say that. And so you can see the MJO, here's the active phase, and it's kind of moving eastward, and then the decaying phase, oh, maybe it just restarted. You'll see it moving eastward. So this is in the GISS, and this is nudged with Mera 2 winds, so in some ways this isn't just like a pure free-running GISS. That's why I can match it up to the NOAA OLR. And you can see that it doesn't quite match the observations, but it generally gets the right, pattern. So here's the dry phase, so kind of the dampened convection, and apparently it dies off in GISS. So here now is then the moisture source that we're, in this case, I made this video literally yesterday, that's associated with the largest magnitude in the OLR anomaly. So that's kind of why it bounces around. Sometimes it'll be associated with the enhanced OLR, sometimes it'll be associated with the most negative OLR. But if we look at the negative OLR in this case, you can tell it's kind of very strongly centered on the convection, but there's also this eastern sort of moisture source. So that could imply, actually we're really not sure, but it could imply that, of course, there's convergence in front of the convective core, which should support this moisture mode, but also that there might be a significant local source, which might even be due to local evaporation under the MJO, maybe driven by, downdrafts or something, or rain re-evaporation. And it's ongoing work. So this is great and all, but there's one major kind of caveat with all these water tracers, or one major question. And that is, they're all model-derived products. Is there any way we can observationally validate or constrain the results? And of course, I can validate the model, right? I can know the model is producing the right precip or the right cloud amount or whatever. But we know that these water tracers are non-unique solutions. So in other words, I can take multiple water tracer sort of values and give you the precipitation. So how do we know which one of these solutions is correct? And this matters because models do produce differences. So this is NCAR's model, this water tracer that I showed earlier, versus the GISS model, doing the same thing. The reason the GISS model looks kind of smoother instead of blocky is because it's using those VSD tracers, the ones that Max developed, where you don't have to specify it ahead of time. Regardless, at first they kind of match up, right? Atmospheric rivers have a shift towards the tropics. They have a decrease in kind of this upper Northeast Pacific. But a significant thing is GISS model shows an increase that's kind of extending way out into sort of the Western Pacific, past the date line, whereas CAM shows almost no change in the Western Pacific. This is kind of a concern because there's some ideas that NCAR's model has an effective length scale that's too small. It tends to rain things out too quickly. And we're not sure why. There's reasons I can talk about if you want, but still, it's gonna be an issue. Sorry, did you have your hand up?
So yeah, so these numbers are, am I reading like a 1% change?
Oh yeah, sorry. You'd have to sum them up to get this. You'd have to sum them up over the area. So this is literally like at each grid point is this value, whereas this value is all of that box summed together. Does that make sense? So you'd have to. I'll show. There's another slide where I have summed them into boxes. But basically, you'd have to map this to these boxes in order to get the same value, and it's going to be larger than because you're summing them together. If that makes sense. Yeah. So this is like every grid box where this is everything in these much larger boxes. But yeah, yeah. So, and in this case, this is like whatever. So this would be like a 10% change, right? 0.1. So, yeah. So they're not huge, but yeah, they are statistically significant. Anyways, so yeah, does CAM seems to show a shorter effective length scale. It seems to not contain this sort of Western Pacific connection, which if there was a real tropical Western Pacific connection, it would matter maybe for even like the forecasting of the amount of water vapor that might be in the atmosphere. So how can I tell which one of these is the right answer? Well, I'm hoping the answer is water isotopes. And if you're not familiar with water isotopes, just take a water molecule and you add a neutron to one of the atoms. So you can have HDO, where one of your hydrogens is deuterium. You're going to have H218O, where you have 2 extra neutrons in your oxygen. This additional mass essentially means that whenever you have a phase change, the amount of these heavier isotopes changes essentially relative to the amount of the standard water H216O. So by kind of recording this sort of change over time, you might be able to say how much kind of water loss has this air mass experienced, and two, what kind of evaporative conditions at the surface it might have also experienced. This is a function of temperature, this ratio. It might say, oh, how much water came from the tropics as opposed to the mid-latitudes. The problem is that even if I did somehow know this part, which is what I want, the original moisture source, all sorts of processes can modify the water isotope values along the way. It can, a lot of times you assume, well, nothing happens and then it rains out right where I am. But in reality, of course, it could experience precipitation before it gets to me, which will change the isotope values. There's mixing along the path. There's cloud microphysics issues that can change the water isotope value. So how much like ice versus how much liquid. All of these can influence the water isotope values, which makes it then hard to really back out what the original ocean value was. But they're still useful. So for example, if you look at the differences between models, so this is the difference in the isotope values for precipitation between GISS and the NCAR model. We find that some areas, like the storm track, and this is in JJA, there's a significant difference. If you're not used to these numbers, 4 to 6 per mil doesn't sound like a lot, but it's a big number for water isotopes. And we know that if you compare the climatologies, there's not much difference, at least for these two runs, between the precipitation amount, the average sort of temperature, at least at the surface, and the general amount of humidity. The actual sort of vertically integrated water vapor is fairly similar between the models. So it's probably not these like on the path events. What we did find though is that the moisture sources are significantly different between the two models. In particular, CAM pulls a lot more moisture from the land, and the GISS model pulls significantly more moisture from the ocean, and particularly the tropical Pacific. This matters because if you then look at the isotope flux from the surface, the oceans tend to be much more positive than the land, as you can see. So maybe this isotope value is driven directly by the difference in the amount of ocean moisture, or tropical ocean moisture, and the amount of land moisture. Sadly, we don't have a lot of observations in the storm track for summer for water isotopes, but in the future, if we do, we will hopefully be able to evaluate which one of these models is more accurate, or at least closer to the observations, and then that might give us confidence as to which one of these sort of evaporation patterns is more correct. Is there more ET from land that's being advected over during the summer, or is there actually more ocean moisture? Finally, that got ruined. Another thing you can do is you can compare the difference between the two isotope values, between two heavy ones, in this case, deuterium and H218O. And in some ways, these values are, the physics isn't perfectly well known about what's driving the this dXS is what it's called, the difference between these two isotope values for any body of water. However, observations have showed that it's not sensitive to all of these along the path processes. In other words, essentially, it's set during evaporation, and then is more or less conserved as it's advected. And so in some ways, this could be the ideal variable, because then if you can know the differences between areas dXS value during evaporation, and if it's not changed during advection or condensation or anything like that, we might be able to then truly back out where the moisture is coming from an observational standpoint. And these are super preliminary. What we found is, and again, even for these atmospheric rivers, that this dXS value decreases as the magnitude of the moisture flux increases, or as the strength of the atmospheric river increases. From the earlier studies, as the strength, I guess I didn't show it, one thing we found is as the strength of the atmospheric rivers increase, the more tropical moisture there is, at least in CAM and NCAR model. And so maybe this dXS value is telling us something that at least we can then compare to observations in the future to determine is the results we're getting from the model about this tropical connection real, or is it, is it all made up? Okay, that's my conclusions. We don't have to read them. So, and I think that's it. So, we can read it, fine. There you go. Yes, but that's it. So it'll be short.
Thank you.
Cool. Ron?
So going back to one of your first slides, you showed, I guess, a composite of moisture transport by atmospheric rivers.
Yeah.
It's way before that, like.
Yeah. It's flow. Okay. Oh.
I should have deferred to people asking questions, but
Hey.
slides toward the end.
Oh, wait. Almost there. Yeah, this one?
Yeah, so that looks a lot like the polar heat transport, and so that suggests like it's extratropical waves that are doing essentially that these rivers are embedded within extratropical waves.
Oh yeah. They
Cyclones, so.
they definitely are. I mean, most of the dynamical studies I've seen have shown that they're essentially always in front of cold fronts,
Right.
which of course then are associated with
Right. So I guess I'm wondering, are atmospheric rivers always associated? Are they a generic property of every extratropical cyclone, just in the way that you get a front, or are some cyclones are these cyclones carrying an inordinate amount of moisture?
Yeah, that's a good question, and the short answer is we don't quite know. So we have found cases where what will happen is, I'll start in the beginning. So these won't form unless there's a extratropical cyclone around. So you need at least one of them to occur. However, what has been found is that one will come through. It'll produce one of these atmospheric rivers, but then this atmospheric river will kind of hang around after the cyclone's passed, and then be available for another cyclone to come through and continue the transport and enhance it or event it. So, so I guess the original convergence that's needed definitely comes from cyclones. But the question is it embedded? Is it like a feature like the warm conveyor belt, which is like embedded into cyclones and is part of it, or is it kind of this secondary thing that's made by the cyclones but isn't necessarily attached to them? We're not really sure. Basically, does that help? Yeah.
So what do you think would happen if we had more moisture? If we had more resolution in the GISS model? I mean, do you think we're going to get more atmospheric rivers, or are we going to get the same number? They're going to be more.
Oh, yeah. Well, so the number I think won't change because, as you said, right, they're associated. Well, I guess it depends, but you can't get more atmospheric rivers than you have cyclones, and so so in terms of the number, the question you would ask is the frequency of cyclones changed due to resolution? And obviously if you're going from 10 by 15 up, it does. But at some point you kind of reach a point where the planetary waves the number of them is the same. And so I guess the number, generally what we found is the number of them doesn't really change. But what does change is the magnitude. The actual amount of moisture flux seems to increase as you increase the resolution. And I've heard that the hypothesis is basically that you're getting better, smaller scale circulation associated with the front itself, like the sort of these. I'm not a frontal expert, but these sort of like mesoscale sort of features that are coming around the front that help enhance the convergence and then help in generate the enhanced moisture flux. There's also a lot of them too are associated with these low level jets. And so, if you improve the dynamics there, it'd also be improved. But from what I've seen, essentially the number doesn't change much, but the magnitude of them does. The intensity of them does. And,
so does that mean you have a greater volume flux because you've got the same number, or is it the volume flux the volume is concentrated into a smaller longitudinal width, and so you're getting the same moisture being transported?
Yeah, that's a great question. I actually don't know. I mean, I think at some point it had to be a decreasing volume, because if you're just increasing the actual amount of water that's being infected as you increase resolution, I mean, I guess I could have them, but at some point you would have very, very wet polar regions and very dry everything else. So, so I think it's my understanding, my guess, my completely not backed up by data guess, is that yeah, you're just getting the atmospheric rivers are getting thinner, but the actual amount of water is the same.
If you go back to like Brian Hill, actually, I'm sorry, Isaac Hill and Brian Soda's paper in 2005 or something about
Oh yeah.
transport. It seemed like there are overall constraints in terms of clouds. There's clapper about how much moisture you can really get transported in a given climate. So it just seems like maybe that might be a constraint in the sense that the total volume really is fixed. And it's just a question of like how are you going to meet that constraint? How are you going to get all that moisture up there?
Yeah, well, we do know from global warming study, or from like climate modeling studies, where you enforce warming, that as you warm the climate, the actual amount of water increases due to Colossus clapeyron. So the actual flux does increase in that case, not just the resolution change. But
well, the point is that flux is determined by the temperature. But the point is it's not kind of a local constraint based on small scale or extratropical cyclone meteorology. It's really kind of a global constraint based on some ways the global mean temperature.
Yeah. No, I think in that case, yeah, you're right. Yeah. I mean, I think we said sort of like the geometry of these features is probably different by the local meteorology, but some ways, if it's really making 90% of the moisture flux, then you have energy limits, right, on what you can do. So globally, so yeah, I think in that case, yeah, it's driven by the global kind of energy budget. Yeah. So in that case, I think Heldon Soden. I mean, I guess their paper focused mostly on the Hadley cell, but
well, they had a new latitude flux also. They argued that should also increase. That should pull more moisture out of the subtropics.
Right. Yeah.
That's probably
A lot of it's just determined by the subtropical temperature because it's not diffusive like temperature. It's because you have your exponential decrease in temperature, and so it's just kind of the subtropical temperature that matters.
Right. Yeah.
It has to increase just.
Yeah. No. So that. Yeah. You're right.
But I was going to ask if these energy constraints are related to this increase in advective length scale, because the idea generally is that the amount of water vapor increases faster than the amount of precipitation because vapor is Clausius clapeyron and precipitation is sort of energetically limited. And so you can sort of think of an increase in the residence time of water vapor in the atmosphere. And so
right, no, that's exactly what's happening.
That essentially?
Yeah, if you just invert the residence time by the velocity, right? If you just take the residence time is increasing and your winds aren't changing that much, then you'll get an increase in the effective length scale.
Right.
So yeah, that's the argument. And so it's not. We found that generally to hold for all in the model, we generally show that this increased length scale holds for everywhere. However, you can imagine that if you increase resolution, there'd be some regions where it wouldn't, depending if the wind speed changes significantly or the effective wind speed changes significantly. So yeah, but basically it's just the inverse of the residence time.
Relatively naive question, but
Sure.
you mentioned that these advective length scales are going to increase with climate change, and so, what defines sort of the maximum length of an atmospheric river? Are you going to get atmospheric rivers that are pulling from, say, the Atlantic and actually cross entire continents and connect over to other parts of the
Right.
What does that look like?
That's a great question, and I don't know if there's I don't know if there's some sort of rigid lid on what the length is in terms of this is the max. I mean, in some ways you can't really be much. I can't imagine to have one that's longer than say a long planetary wave. So in some ways I feel like that would be the limit.
You guys couldn't do an Eocene experiment or something?
Well, potentially. So we'll see. Yeah, so we'll test. So we're gonna do some paleoclimate runs with really hot climates, and so we'll see if does it just keep going or does it kind of taper off at some point, and then.
Well, I guess the one question is is this length scale? I mean, is it changes? Is this change in the vertical direction or is it in the zonal direction?
Yeah. I mean, well, we have found that it seems to be both zonal and meridional increase in their effective length scale, but what we don't know is if one. Yeah, I don't know if one increases more or less than the other. So if you get more meridional or more zonal or whatever. So. But that's a good question. I actually don't know if there's some sort of limit to the length scale from like a theory point of view. Cool.
Thanks, Jesse. That was
Thanks.